We know three states of matter, that is solids, liquids and gases. And also we studied about the force of attraction between the particles in these three states. When the molecular forces of attraction between the particles of a matter are minimum, the particle exists in a state which is known as gaseous state, or we can say in gaseous state the molecules are far away from each other and free to move in available space. And among these three states of matter, the gaseous state is the simplest and shows greatest uniformity in behavior. The behavior of gases can be described by certain quantitative relationships between mass, pressure, volume, and temperature. These relationships are called gas laws. Before going to gas laws, let us discuss the important postulates related to kinetic molecular theory of gases. All gases are made up of molecules moving randomly in all the directions. Suppose we consider this is a gas sample. Here you can find this gas is made up of molecules which are moving randomly as are seen in the figure. The volume of individual molecule is negligible as compared to the total volume of the gas. What does it mean? Suppose you consider this is a container. The volume of this container is in order of centimeter cube. If we consider the volume of a molecule, it is in order of Fermi cube. That is 1 Fermi equal to 10 power minus 15 meter. That means if you compare the volume of container, the volume of the molecule is very small. It is around 10 power minus 45 times of that of the container. That means the volume of the container is 10 power 45 times more compared to the volume of the molecule. Pressure exerted by gas is due to the collision of gas molecules with the walls of the container. Gas pressure is due to the collision of molecules with the container. Therefore, we can say the pressure is directly proportional to number of collisions per unit time per unit area by the molecules on the wall of the container. If gas is having more number of molecules, we can expect that gas is having more pressure. More number of molecules means more density. That means if the gas pressure is more, the density of gas is also more. If the density of gas is more, the pressure is also more. That means the pressure is directly proportional to the density of the gas. All collisions between two molecules or between a molecule and a wall are perfectly elastic. What is the meaning of perfect elastic collision? Perfectly elastic collision is a collision in which the momentum is conserved and the kinetic energy is conserved. That means during a perfectly elastic collision, there is no loss in kinetic energy. The collisions between the molecules of a gas are perfectly elastic. That means during the collision, they doesn't lose any energy or they gain energy. All these collisions are perfectly elastic, and during this collision, there is no change in shape, size or energy of the molecule. The next postulate is all the molecules obey Newton's laws of motion. Already you know Newton's laws of motion. In your previous classes you studied. All molecules, they obey Newton's laws of motion. Gas molecules neither attract or repel each other. The gas molecules, they never attract or repel. That means they are neutral in nature. Kinetic energy of the molecules depends upon the absolute temperature. That is, kinetic energy directly proportional to absolute temperature. In general, the kinetic energy of the molecules, they depend on motion of the molecules. As the temperature increases, the vibrations of the molecules increases, it increases the kinetic energy. Therefore, we can consider the kinetic energy is directly proportional to absolute temperature. The force of gravity has no effect on speed of gas molecules. Since the mass of the gas molecules is very less, very negligible, there is no effect of gravity on the speed of gas molecules. These are the postulates of kinetic molecular theory of gases. Before going to gas laws, we discuss about some measurable properties or parameters of gases. The physical behavior of gases can be described by four variables. They are volume, temperature, pressure, mass, and these are known as standard variables. The relation between these variables is almost common for all gases. By knowing these variables, you can give the behavior of a gas. The first one is mass. The mass of gas is denoted by m, and this is related to number of moles, number of particles that present in a gas. And the number of moles n equal to mass in grams by molar mass, that is small m by capital M. Therefore, we can write mass of the gas in grams is equal to number of moles into molar mass. The next one is the volume. Gases occupies whole space available to them. The volume occupied by a gas, this is equal to the volume of the container. The volume of gas is denoted by V, and it is measured in units of liter or cubic meter or cubic centimeter or cubic decameters. 1 liter equal to 1000 centimeter cube, or this is equal to 1000 milliliters. Pressure. Pressure is nothing but the force that gas exerts per unit area on the walls of the container. That is, pressure is force by area. Now this is equal to mass into acceleration by area. The unit of pressure is Pascal. It is also measured in terms of height of mercury, that is centimeters of mercury or millimeters of mercury, bar, tor, all these are units for pressure. In general, the atmospheric pressure is represented by ATM. 1 ATM means 1 atmosphere pressure. This is 76 centimeters of mercury, or this is equal to 760 millimeters of mercury, or this is equal to 760 tor, or this is equal to 1.013 into 10 power 5 Pascal. Another parameter is the temperature. It is denoted by T. It is defined as the degree of hotness or coldness of the body, and the units of temperature are K, which stands for Kelvin, degree Celsius or degree Fahrenheit. We know the relation between these three scales. The relation between these three scales is given by F minus 32 by 180. This is equal to C by 100. This is equal to K minus 273 by 100. And now we discuss about gas laws. The behavior of gas under known conditions of pressure, volume, temperature is described by laws which are known as gas laws. First one is the Boyle's law. This law was given by Robert Boyle in 1622, and this states that at constant temperature, the volume of a certain amount of gas is inversely proportional to pressure exerted on it. That is, if V is the volume of gas under pressure P at a fixed temperature, V is directly proportional to 1 by P, or PV equal to constant. This is Boyle's law. Now you take a container, as I was saying in the figure, which is filled with gas. This contains a piston. When you press the piston, then what happens? Yes, the volume of gas will decrease. If you go on apply pressure on piston, the volume of gas decreases. Here you are applying force means you are applying pressure. You are increasing pressure. With increasing pressure, what happens to volume of the gas? Yes, it decreases. If you decrease the pressure applied, the volume of gas increases. Then what relation you can give between pressure and volume? Yes, pressure is inversely proportional to volume. This is nothing but Boyle's law. And this is applicable at only constant temperature. Why only at constant temperature? Already we know that the rise in temperature also expands the gas. The volume of a gas also depends on temperature. Therefore, this law is applicable only at constant temperature. Consider a given amount of gas occupy volume V under pressure P1 and changes to volume V2 under pressure P2 and so on. The product of PV is constant. Therefore, we can write P1V1 equal to P2V2 equal to P3V3 equal to etc. And this is equal to constant. The graphical representation of Boyle's law, just you take the same experiment, pressure volume relation. You can find a graph pressure versus volume for a gas as are saying in the figure. To show the relation between pressure and volume, we are taking volume on x-axis and pressure on y-axis. Say here, with increasing volume, the pressure will decrease. This can be represented using a graph like this. If the volume increases, then pressure will decrease. Now this is the graph P versus 1 by V, taking 1 by V along x-axis, pressure along y-axis. It is a straight line passing through origin. If we take a graph taking log V along x-axis, log P along y-axis, we get a graph, and this graph with increasing pressure, volume decreases, with increasing volume, pressure decreases, and it is a straight line. Suppose we draw a graph PV versus P, taking pressure along x-axis, the product of pressure and volume along y-axis. Then how you get the graph? PV equal to constant. Therefore, this graph is a straight line which is parallel to x-axis. And another law is Charles' law. This law is given by scientist Charles, and it states that at constant pressure, the volume of certain amount of a gas is directly proportional to absolute temperature of the gas. Now you see this experiment. Here I am applying the constant pressure. This piston is kept constant with constant force. If you heat it, that means if you raise the temperature of this gas, then what happens? Exactly, it expands. If you give more and more heat, the rise in temperature is more. The volume is also more. From this, what you can conclude? The pressure is constant. The volume of gas is directly proportional to the temperature. This is Charles' law. Mathematically, V proportional to T or V by T is equal to constant. And very important thing, here T is the absolute temperature. That means this is taken in Kelvin scale, not in degree Celsius. This is also called constant pressure law of Charles. Suppose we consider at constant pressure, the volume of gas is V1 at temperature T1, V2 at temperature T2, V3 at temperature T3 and so on. Then we can write V1 by T1 is equal to V2 by T2. This is equal to V3 by T3, etc. This is equal to constant. Now we take the graphical representation of Charles' law, taking temperature along x-axis, volume along y-axis. Already we know that as temperature increases, the volume of the gas increases. Therefore, this graph is a straight line passing through the origin. At T equal to 0, that means at absolute 0 temperature, the volume of the gas is 0. All gases occupy 0 volume at absolute 0 temperature. And this is a graph taking 1 by T along x-axis and the volume along y-axis. Since Vt equal to constant, this graph we get a straight line having negative slope. If we draw a graph, log V versus log T, taking log T along x-axis and log V along y-axis. As V proportional to T, log V proportional to log T, it is also a straight line. If we draw a graph, taking temperature along x-axis, V by T along y-axis. Already we know that V by T equal to constant. Therefore, this is a straight line which is parallel to temperature axis, that is x-axis. Next one is Gay-Lussac's law. This is also called constant volume law of Charles. This law is given by Gay-Lussac and it states that at constant volume, the pressure of a gas is directly proportional to its absolute temperature. Now you consider this container with piston. If you give the temperature to this gas, already we know that because of the temperature the gas will expand. I want to retain the same volume. Then what I have to do is I have to apply more and more pressure on this. From this what we can understand? The pressure what you are applying is directly proportional to temperature to keep a constant volume. That is, at constant volume, the pressure is directly proportional to absolute temperature. And this is Gay-Lussac's law or Charles' second law. Charles' first law gives the relation between volume and temperature. And this law gives the relation between pressure and temperature. That is P proportional to T or P by T equal to constant. If we consider for a gas at constant volume, P1 is the pressure at temperature T1, P2 is the pressure at temperature T2 and so on. Then you can write P1 by T1 is equal to P2 by T2, this is equal to P3 by T3 and this is equal to constant. And graphically this can be represented like this. If you draw a graph at constant volume, taking temperature on x-axis and pressure on y-axis as P proportional to T, you get a straight line which is passing through the origin. From this graph, we can understand at T equal to 0, that is at absolute 0 temperature, the pressure of the gas is equal to 0. Similarly, this is the graph P versus 1 by T, taking 1 by T along x-axis and pressure along y-axis at constant volume. We get a straight line having negative slope. If we draw a graph taking log T along x-axis, log P along y-axis, we get a straight line. Since P proportional to T, we can also write log P proportional to log T. Now this is a straight line passing through the origin. If we draw a graph taking temperature along x-axis, P by T along y-axis, since P by T equal to constant, we get a straight line which is parallel to x-axis, that is temperature axis. The next law is Avogadro's law. This law is given by Avogadro in 1811 and it states that at constant temperature and pressure, the volume occupied by the gas is directly proportional to the number of moles or the number of molecules of the gas. According to this law, if temperature and pressure is constant, the volume depends on the number of molecules that present in the gas. See here, if you go on increase the number of molecules, what happens to volume? As definitely it increases. According to this law, V proportional to small n, where small n, this is number of moles, this is nothing but mass by molar mass. That is V proportional to small m by capital M. The graphical representation of this law. As V proportional to n, if we draw a graph taking n along x-axis, volume along y-axis, we get a straight line which is passing through origin. Similarly, if we draw a graph taking n along x-axis and 1 by v along y-axis, we get a straight line having negative slope as I was saying in the figure. And next we derive ideal gas equation. This equation helps us to find the variation of volume when the terms pressure, temperature and the number of moles they vary simultaneously. All gases obey Boyle's law and Charles' law at low pressures and high temperatures. The gases which obey the above laws at all pressures and temperatures are known as ideal gases. An ideal gas equation gives the relation between the pressure P, the volume V and absolute temperature T for a given mass of a gas. We know that from Boyle's law, V proportional to 1 by P, and from Charles' law, V proportional to T, from Avogadro law, V proportional to small n. If you combine these three laws, we get an equation V proportional to Nt by P, or V equal to nRT by P, or PV equal to nRT. This is ideal gas equation. This N is the number of moles. R is called universal gas constant. The value of R is 8.314 joule per mole per Kelvin in SI system. It is 8.314 into 10 power 7 egg per mole per Kelvin in CGS system. 0.0821 liter air pressure per mole per Kelvin. This is the practical value and this is equal to 2 calorie per mole per Kelvin. This is the value of universal gas constant.